So welcome back. So we are in section 4, chapter 5, and we're gonna talk a little bit about the calculus of exponential functions. Now, as an aside, and there will be lots of asides in this lecture, but as an aside, I want to show you a couple things, point out a couple things. So, mathematicians are extremely interested in shortcuts, right? You guys know what I'm talking about? Any Alt-Tab keyboarders out there, right? You know what I'm talking about, shortcuts, right? And things to make life easier. So, in fact, look, multiplication was created as a shortcut for addition, right? So, instead of 3 plus 3 plus 3 plus 3 10 times, right? You could just do 3 times 10. Right, so it's a shortcut. Or some, mathematicians are fairly lazy. If you are thinking about if you have to multiply, and say you have 3 times 3 times 3 times 3, 10 times. Well, exponential functions are a shortcut for multiplication, right? So multiplication, shortcut for addition, exponential function, shortcut for multiplication. So you could do 3 to the power of 10. Okay, so when it comes to exponential functions, so just, again, any operation to a mathematician is going to want to know what the inverse is, right? We want to know how to go back. We want to know about subtraction after you've told us about addition, right? So let's take a look at two graphs here. Let's start with the geometry, because I firmly believe the geometry portion is what's missing. We spend too much time doing equations and algebra stuff, and not enough time with the graphs. So look, this is the graph of e to the power of x, right? This is an exponential function, right? It is, in other words, it's exponentially growing. Makes sense? This is what we want in our bank accounts and investments, right? We want our this is how we get massive growth. This is what we don't want when it comes to zombie apocalypses, right? This is, in other words, everyone's running in zombie movies because zombies are growing exponentially. They're actually logarithmic because there's only but so many humans on Earth, right? But nevertheless, you get the idea. Everybody's running in zombie movies because of the rate of growth, right? Because look, if zombies were increasing linearly, no one would give a crap. But because they are increasing exponentially, this means, notice, do you see, look. Don't act like you're not interested. You see that slope, right? Do you see how, now if I were to draw a slope here, do you see how the slopes, that's a horrible, how dare you let me do that? Look, you see this line here? If you were walking up that mountain, that's kind of steep. But if you were to pick a point over here, you see how it's a little bit steeper? Right? Quite a lot steeper. So, in other words, the slopes are actually increasing. How do I state that? The rate of change is increasing, right? So, that's what we mean by exponential. So, beautiful graphs. All right, well, again, we need inverse operations, and if we're going to talk about e to the power of x, well, look, logarithms are a way of are the inverses for exponentials. I'll say that again. So if you have b to the power of x, if that gives you something, some y value, then you can use logarithms, right, to, my apologies, I messed that up, logarithms of, I'll rewrite that because I didn't hold my stylus long enough. So logarithms are a way of, are the inverse function for exponential functions, right? So if you want a way of getting back to where you started or undoing, you would need logarithms. So now look, in case someone has, not taken the liberty to tell you, ln is just a logarithm, right? It's just log, but it has a base of e, right? It's a logarithm with base e, but since it's so useful, we give it its own, its own button on a calculator, if you will, right? And we denote it with ln, but it is a logarithm. This is ln of x. It's just a logarithm. So here is the graph of e to the x. Here is the graph of ln of x. And these are inverse. You can see the symmetry, right? Can't you see the symmetry along that y equals x line? See how you could fold it, right? Mirror image, like you just fold it right on top over that line. So they are inverses. And if we start with some information, right? So we'll start with ln. So let's look at this graph here. So the domain. Let's think about the domain for ln. Right. So notice that this graph domain, we're looking at x values, right? So notice that this graph gets really close to x equaling 0, but it never actually gets there, right? Like a pilot that never gets really close to the runway but never lands. This is what we're looking at. So the domain gets as close as you want to 0, but it doesn't ever actually get to 0. So notice I'm using the parenthesis. And then it can proceed to infinity. All right, now let's look at the range. All right, so again, the range of our logarithm. So if we're looking at range, we're looking up and down, we're looking, the y values. So notice that this graph would continue to go down to negative infinity, and this, if you were to extend this out, this would continue to go up to positive infinity. So the range is from negative infinity to positive infinity. Okay, so now you and me, since we're not going anywhere, right, we're stuck with each other, let's look at the graph of e to the x, and let's see what we can notice. So do you agree with me, first off, do you agree with me that if you were to extend this line indefinitely, that this would be going in the negative direction, this line would continue to go in the negative direction and would continue to go in the positive direction? I'll say that again. The domain, we're looking left to right, okay? We're not looking up and down. We're looking left to right. So if you keep drawing this graph, it'll go towards the negative infinity direction, and if you keep drawing this graph, it'll continue going in the positive direction to infinity. So the domain of e to the x is from negative infinity to positive infinity. All right? Now let's look at the range. So look, now we're looking up and down. So notice that this graph will never actually touch y equals 0, right? It'll keep, it'll just keep getting closer and closer and closer and closer to y is 0, but never actually touches y is 0. And then it will also, if you're looking, to the right, it'll also continue to go up to infinity. So the range is from 0 to positive infinity. And now, do you see how the domain maps to the range maps to the domain, right? Do you understand? Do you see how this domain for ln is the range for e to the x, and the domain for e to the x is the range of ln? That's why if you like the x's and y's swap, right? That's why there's symmetry about that line x equals y. Okay, now what is the point of this? So the point is, just definition of the natural exponential function, right? This e to the x, and what we're stating is that they are indeed inverses. So if they are inverses, do you remember in the previous lesson, remember how if you had f of g of x and you get x, that's telling you they're inverse functions? Then you can see how ln of e to the x is just x, or e to the ln of x is just x. So these are indeed inverse functions. Okay? Now where are we going with this? Well, I have to, I'll get you there, but first, if you don't mind, if you have enough energy, walk with me back in time a little bit, right? So let me tell you, how in all of our subjects, right, we all have our heroes. We hero worship, and mathematics is the same. And I will tell you that Euler is my favorite mathematician, right, of antiquity. Well, not really of antiquity. We're looking back in, man, my math history is going bad. So, 400 years, something like that. 300 years? No, goodness gracious, please. I will have to correct myself for this. Yeah, anyway, a while ago, right, before I was born. But let me tell you a little bit about Euler. Euler is, how do I put it? An interesting individual, but let me start with some accolades, right? Some accomplishments. Now, for most mathematicians, right? And I'm talking about at your Ivy League schools, or wherever. If you can publish, let's say, one journal, peer-reviewed journal entry, if you can some publication, if you can publish maybe one a year, every 2 years, you're on par. You're doing great. Euler was so prolific that he was still publishing mathematics in journals for 10, 15 years after he died, right? So in other words, after he died, he still published another 200 peer-reviewed journals in mathematics. They were they were so backlogged going through his work and that he was still publishing after his death. Just to kind of give you a breath of how prolific this individual. I mean, we're something like 60,000 pages of mathematics over 12 volumes, right? So just insanity. It's what's more insane. It's just, well, I'm going to waste quite a few minutes of your life, right? If we're going to talk about Euler, let's do it. You probably had, I think at least 100 math definitions are named after Euler. And in fact, the symbol E, which is what we saw on the previous page, was first used by Euler. So now, the sheer breadth of his contribution is insane enough. To kind of give you a little bit more of a backdrop, so he spent the majority of his adulthood, if I recall correctly, blind in one eye. I don't know that he was born blind in one eye, but that I can't recall. But I know by the age of 50, he was blind in both. He was blind in both eyes. Now you would think that becoming blind would slow the contributions from Euler, but it actually didn't. It actually increased how much he published. He would have individuals follow him around and write down and translate some of his ideas that were going on in his head. I will give you one. I'll try one more way to show you how unbelievably genius this individual was. So there's a concept in math called a proper divisor. I can show you really quickly. So if I were to ask you what divides into 6, right, you would say, well, 1 can go into 6, 2 can go into 6, 3 can go into 6. These are the proper divisors. Okay? Proper divisors. Now, notice I could add these up if I wanted to. I could add up the proper divisors. Well, now let me show you about, or tell you about what we call amicable numbers. So numbers, we would say that two numbers are amicable if you were to list all the proper divisors, right, just like I did up here with 6, if you were to list all the proper divisors of, let's say, 220 and 284, if you were to add all the proper divisors of 220, and then you were to add all the proper divisors for 284, what's interesting is the sum of all of these divisors for 220 adds up to be 284. The sum of all the divisors for 284 adds up to be 220. Okay? So this is truly a pair, right? This is a match made in heaven, if you will. In fact, my wife, for Valentine's Day, I bought her a necklace where, I believe it was a necklace with the number 220, and of course I had the number 284, right? Because I'm pair, right? I hear you. I see you about to steal my idea. All right, I understand. Okay, now listen. So, do you understand? I hope you understand that these are amicable numbers, but you don't even have to understand that to understand this. So, by the 1700s, there were only a handful. I think there was only 3 known amicable numbers. Right, here's one pair. That's one of them. There was 2 more. There's only 3 known. So someone decides to give Euler, right? He's going home for the weekend. Hey, Euler, why don't you give it a shot, man? Why don't see if you can find us some more amicable numbers? We only got 3 of them. Well, Euler comes back, right? His Majesty shows up Monday. Oh, my sincere apologies. I was only able to find 58 more, right? So we spent, 2,000 years of mathematics only being able to find 3 amicable numbers. And Euler, in the breath of an extremely short time, was able to contribute another 58, I believe, if I recall correctly. I will no longer, I'll tell you the very last thing about my best friend here, Euler. His identity, all right, Euler's identity. This is, sometimes you'll see these surveys. This is ranked the most beautiful equation in all of mathematics, probably by people who don't understand mathematics, but very well could be people that do, because this is one of the most beautiful. Well, it's just a strange reality that, the number pi, the number e, the imaginary number 1, 0. These are separated by millennia, right? They're separated by thousands of years of discovery, and the fact that they can all fit into a little equation for which, when you add them up, you get 0 it's just an amazing feat, right? So this is his great, I don't know if you would say this is his greatest contribution, but this is probably his most well-known contribution, right? Anyway, if you follow me to differential equations, we will see this again. I will show you how this comes about. But right now we need some more training. So I've wasted a lot of time talking about an ancient mathematician, not necessarily ancient, but and what I'll do is I'll do example 1, example 2, which is really just pre-calculus skills, and then we'll take a break, and when we'll come back, I will get into some of the calculus of this stuff. So let's start with the first example. So all we want to be able to do is solve this exponential equation, right? In other words, we want it to, the word solve, right? We want to be able to make a statement x equals when we're done. So how do we do it? Well, first we just go ahead and write the equation. So we have 7 is equal to e, and this might be hard to see on your end, but this is e to the power of x plus 1. Okay? So there is some x out there that when you plug it in, e to the power of x plus 1 is equal to 7. We're trying to figure out what that x value is. All right, well, what we're going to do is we're going to use, remember, I'm going to go back a page there too. Notice how that you can cancel using those inverse relationships. Ln of e to the x is just x, or e to the ln of x is just x. We're going to use that to our advantage because right now your variable is stuck inside of an exponent. This is not an algebraic problem, right? You can't use algebraic techniques to solve this problem. So, but what we're going to do is we're going to use, we're going to take ln of both sides. So we're going to take ln of 7. And if you're going to take ln of one side, you're going to have to take ln of the other side. All right, well, let's see what we have here. So do you recall there's a little operation in a property, a logarithmic property, that basically says that if you have, let's say, log of m to the power of x, you can rewrite that, right? Just we're bringing the x out front here. You can rewrite that as x log of m, right? So just a property of logarithms. So that is exactly what we're going to do here. So since we have ln of e to the x plus 1, we're going to be able to take that whole exponent and we're going to be able to move it out front. Okay, so let me write what that looks like. So now I have ln of 7 is equal to x plus 1. And let's see what's left. What's left is ln of e. You could say e to the power of 1 if you wanted to, but it's just ln of e. So look, ln of e, e to the ln, right? Square root of 9, 3, square root of 9, 3 squared. Those are just inverse. They cancel. This turns into 1. Ln of e is just 1. So what's left at that point is just ln of 7 is equal to x plus 1, right? So I'll write you a note. So just in case it's been a while, this is equal to 1. All right, remember, the goal is to solve. So x equals is our goal. Well, the only thing, if you want to get x by itself, all we got to do is just subtract 1, and there we have it. So x is equal to ln of 7 minus 1. And I'll go ahead and get rid of that last parenthesis. There's no need to have that. So there you have it. So if you were to plug in ln of 7 minus 1 in for x, what you would have when all is said and done is 7, right? And you should check to make sure that you did everything correctly, especially when you're dealing with logarithms, because there are what's known as extraneous solutions, right? Where you do want to always kind of double check that you've that everything works out, because if you don't know what I'm talking about with extraneous solutions, sometimes you can solve a logarithmic, let's say a logarithmic equation, and you can end up with x equals, and you did everything mathematically, you did everything perfectly, but this, whatever this x is, was restricted from the domain at the beginning. So you always want to double check that things make sense. So one more problem, then we'll take a break. So now we want to solve a logarithmic equation. So again, the goal is to make a statement about x equals. Okay, well, just like here we took ln of both sides, here we're going to what we call exponentiate both sides. So it's going to be e to the power of. Ready? So this would be e to the power of ln of 2x minus 3 and e to the power of 5. So that's the exponentiate our equation. So e to the power of. And now let's see what happens here. So if you recall, anytime you have e to the ln or ln of e, they are going to cancel each other. All right, so at that stage, all we have, and I'll just write you a note, this e to the ln is just equal to 1. So all that you have left is just 2x minus 3 is equal to e to the power of 5. So notice how using those properties, we were able to go from logarithmic or exponential back to algebra, because I can now solve this. This is an algebra problem. I can get x by itself. All right, well, I got to get rid of the 3, and then I got to get rid of the 2. So we'll do it in 2 steps. So 2x, to get rid of 3, I got to add it. So e to the 5th plus 3. And if you want to undo times 2, well, you divide by 2. So x is equal to e to the power of 5 plus 3 over 2. All right. So really quickly, and then we'll take our break. So this is the answer. This is the answer. If you give me something like, x equals 75.707, some decimal approximation, right? If you turn this into a decimal onto a test, then I'm going to take off points, right? Because you're not allowed to just you're not allowed to take solutions and just start approximating, right? Because you don't even know what you're allowed to round. You don't know the margin of error you're even allowed to have, right? So you don't get to just turn things into decimals just because. They're in mathematics. In mathematics, both of us can be wrong, but we can't both be right. So this is the solution, and anything else is not. Okay? This subject is, the one beautiful thing about this subject is it does not forgive you for any mistake, right? So please leave your answers in exact form. Please don't round. Don't round stuff. Don't round at all, in fact, until, I know in your engineering and science classes you have to round, but at least there somebody tells you what type of error they're willing to accept. Anyway, I will see you guys in the next video. Take care.